For this video, we'll be reading Chapter 8, Section 1, Mass Movement at Earth's Surface, page 181. Every day, the landscape around us undergoes changes. If you compare old and new photographs of the landscape around your home, you might have to look very closely to notice some of the subtle differences. Other changes, such as landslides, occur quickly and have very noticeable immediate effects. Mass movements. How do landforms such as mountains, hills, and plateaus wear down and change? Landforms can change through the process involving wind, ice, and water, and sometimes through the force of gravity alone. The downslope movement of loose sediments and weathered rock resulting from the force of gravity is called mass movement. In the development of most of Earth's landforms, erosion is the step that follows weathering. After weathering processes weaken and break down into rock into smaller and smaller pieces, mass movements may occur and carry the debris downslope. Because climate has a major effect on the vegetation and the weathering activities that occur in a particular area, climate conditions determine which materials and how much of each will be made available for mass movement. All mass movements occur on slopes. Because very few places on Earth are completely flat, most all of Earth's surface undergoes mass movement. Mass movement range from extremely slow motions to sudden slides, falls, and flows. The Earth's materials that are moved range from fine mud to large boulders. Variables that influence mass movements. Several variables influence the mass movements of Earth's material. One variable is the material's weight resulting from gravity, which works to pull the material downslope. A second variable is the material's resistance to sliding or flowing. A third variable can be a trigger, such as the earthquake, that works to shake material loose from a slope, as shown in Figure 8.1a. Mass movement occurs when the force working to pull material down a slope are stronger than the material's resistance to sliding, flowing, and falling. Some common types of mass movement are illustrated in Figure 8.1b. Erosion and the undermining of soil at the foot of the slope increase in the potential of earth materials to move downhill, as does the increased weight from torrential rainfall. An important force that determines a material's resistance to downhill movement is friction between the material and the slope. Water is a fourth variable that influences mass movements, as illustrated in Figure 8.2. On a slope, too little water may prevent sediment grains from holding together at all, thereby increasing the material's potential for movement. You could demonstrate this concept by trying to form dry, loose soil into a ball. It would be difficult to get the particles to hold together. However, if you added small amounts of water, the particles of soil would cling together and remain in the shape in which they are formed them. Similarly, the addition of water to sediments on a slope helps to hold the grains together and makes the material more stable. On the other hand, too much water can make a slope unstable. Saturation by water greatly increases the weight of soils and sediments. In addition, as the water fills the tiny open spaces between grains, it may act as a lubricant between the grains to reduce the friction between them. Thus, the force of gravity is more likely to pull the saturated material down. While water is very important to the process of mass movement, it is important to note that water is not involved as a transport agent. In a mass movements, water moves along with Earth's minerals. This is in contrast to steam transport, in which sediment moves along with the water. Types of mass movement. Mass movements are classified as creep, flows, sliders, and falls. Mass movements can move different types of materials in various ways. Let's investigate the different types of mass movement. Creep. The slow, steady downhill flow of loose, weathered earth materials, especially soils, is called creep. Because movement may be as little as a few centimeters per year, the effects of creep usually are only noticeable over long periods of time. One way to tell whether creep has occurred is to observe the positions of structures and objects. As illustrated in Figure 8.3, creep can cause the tilting of one's vertically utility poles, fence, and gravestones, the bending of trees and cracking of walls, and the breaking of underground pipes. Loose materials are also on almost all slopes. Even the very gentlest undergo creep. Soil creep moves huge amounts of surface materials each year. The slow downhill movement of loose water-logged materials that occurs in regions of permafrost is called sulfication. The material moved in sulfication is a mud-like liquid that is produced when water is released from melting permafrost during the warm seasons. The water saturates the surface layer of soil and is unable to move downward through the underlying permafrost. As a result, the surface layer can slide slowly down a slope. Solidification may also occur in human regions where the underground remains saturated year-round. Flows. In some mass movements, Earth's materials flow as if they were a thick liquid. The materials can move as slow as a few centimeters per year or as rapidly as hundreds of kilometers per hour. Earth flows are moderately slow movements of soils, whereas mud flows are swiftly moving mixtures of mud and water. Mud flows may be triggered by earthquake or similar vibrations and are common in volcanic regions where the heat from a volcano melts snow on nearby slopes and that has fine sediment and little vegetation. The meltwater fills the space between the small particles of sediment and allows them to slide readily over one another and move down the slope. As shown in figure 8.4a, when Mount St. Helens erupted in 1980, it triggered mud flows and traveled downhill at speeds at over 30 kilometers per hour. Although the area was sparsely populated, the mud flows damaged or destroyed more than 200 homes. In 1998, a mud flow in Italy caused many deaths and much destruction, as shown in figure 8.4b. Mud flows are also common in sloped, semi-arid regions that experience intense, short-lived rainstorms. The Los Angeles Basin in Southern California is an example of an area where mud flows are common. In such areas, periods of drought and forest fire can leave the slopes with little protective vegetation. When heavy rains eventually fall in these areas, they can cause massive disruptive mud flows. Mud flows are destructive in areas where urban development has spread to the bases of mountainous areas. Slides. A rapid downslope movement of earth materials that occurs when a relatively thin block of loose soil, rock, and debris separate from the underlying bedrock is called a landslide, illustrated in figure 8.5a. The material rapidly slides down slope as one block with little internal mixing. Some landslides may reach speeds of 200 kilometers per hour, as shown in figure 8.5b. A landslide mass eventually stops and becomes a pile of debris at the bottom of the slope, sometimes damming rivers and causing flooding. Landslides are common on steep slopes, especially when soils and weathered bedrock are fully saturated by water. This destructive form of mass movement causes almost $2 billion in damage and several deaths per year in the United States alone. You will explore the movement of a landslide in the Mapping GeoLab at the end of this chapter. A rock slide is a type of landslide that occurs when a sheet of rock moves downhill on a sliding surface. During a rock slide, relatively thin blocks of rock are broken into smaller blocks as they move downslope. Often triggered by earthquakes, rock slides can move large amounts of material. Slumps, as illustrated in figure 8.6a, when the mass of material in a landslide rotates and slides along a curved surface, a slump results. Slumps such as the one shown in figure 8.6b may occur in areas that have thick soils on moderate to steep slopes. Sometimes slumps occur along highways where the slopes of soils are extremely steep. Slumps are common after rains, when water reduces the frictional contact between grains of soil and acts as a lubricant between surface materials and underlying layers. The weight of the additional water pulls materials downhill. As with other types of mass movements, slumps can be triggered by earthquakes. Slumps leave crescent-shaped scars on slopes. Avalanches. Landslides that occur in mountainous areas with thick accumulations of snow are called avalanches. Avalanches usually occurs on slopes at least 35 degrees, and about 10,000 avalanches occur each year in the mountains of the western United States alone. Radiation from the sun can melt surface snow, which then refreezes at night into icy crusts. Snow that falls on top of this crust can eventually build up, become heavy, slip off, and slide down a slope as an avalanche. Another type of weak snow layer forms in early winter as the ground, which is still warm, melts the overlying snow. The snow then refreezes into a layer of jagged, slippery snow crystals. A vibrating trigger, even from a single skier, can send such an unstable layer sliding down a mountainside at speeds of about 300 kilometers per hour. As shown in figure 8.7, avalanches pose particular risks in places such as Switzerland, where more than 50% of the population lives in avalanche terrain. In the 1998-1999 season, for example, hundreds of major avalanches swept down the Swiss Alps. Rock falls. Rock falls commonly occur on high elevations in steep road cuts and on rocky shorelines. On high cliffs, rocks are loosened by physical weathering processes such as freezing and thawing and by plant growth. As rocks break up and fall directly downward, they may bounce and roll, ultimately producing a cone-shaped pile of coarse debris called talus. At the base of the slope, on human-made rock walls, such as road cuts, rock falls are particularly common. Falling rock warning signs can often be seen along highways that run through steep, rocky areas, as shown in Figure 8.8. Rock falls are less likely to occur in humid regions where the rock is typically covered by a thick layer of soil, vegetation, and loose materials. Mass movements affect people. While mass movements are natural processes, human activities often contribute to the factors that cause mass movements. Activities such as constructing heavy buildings, roads, and other structures can make slope materials unstable. In addition, poor maintenance of septic systems, which often leak, can trigger slides. Dangerous mud flows. Humans' lives are in danger when people live on steep terrain or in the path of unstable slope materials. For example, in December of 1999, northern Venezuela experienced the heaviest rains that had fallen there in 100 years. Within several days, between 30 to 45 centimeters of unseasonal rainfall occurred in this area. The sudden saturation of sediments, combined with the area's steep topography and widespread deforestation, resulted in several mud flows and landslides, as shown in Figure 8.9. Tens of thousands of people died. More than 114,000 people were left homeless, and 23,000 homes were destroyed. Entire villages were buried in mud, rock, and debris. The widespread loss of human life was primarily a result of the location of villages both high up in steep terrain and at the foot of unstable, saturated slopes, reducing the risks. Catastrophic mass movements are most common on slopes greater than 25 degrees that experience annual rainfall of over 90 centimeters. The best way to minimize the destruction caused by mass movements is to avoid building structures on such steep and unstable slopes. Prevention actions. Although preventing mass movements disasters is not an easy task, some actions can help to avoid the potential hazards. For example, a series of trenches can be dug to divert running water around a slope and control its drainage. Other approaches to controlling landslides include covering steep slopes with materials such as steel nets. The construction protective fences along highways and areas where lock slides are common, as shown in Figure 8.10. Still, other approaches involve the installation of retention walls to support the bases of weakened slopes and prevent them from falling. Most of these efforts at slope stabilization and prevention of mass movements, however, are generally successful only in the short run. The best way to reduce the number of disasters related to mass movements is to educate people about the problems of building on steep slopes.